So this is Unit 1, Lesson 7 in the AP Calculus curriculum. The unit is called Limits and Continuity. The lesson is called Selecting Procedures for Determining Limits. So in this lesson, we're going to learn a few algebraic and trigonometric ways of working with the functions to rewrite the functions so that we can use direct substitution to find limits of different functions. And we're just going to use three select methods that we're going to look at, three common ways. So factoring out and canceling common factors in the numerator and the denominator, rationalizing the denominator, and then looking at some trig identities to simplify some functions. And so I hope you enjoy the memes right there. Some examples. So here's how we can evaluate limits with direct substitution by factoring. So if I look at the first example, the limit as x approaches 2. If I try using direct substitution, I'm going to get 0 in the denominator. And if I take 2 in the numerator, I'm also going to get 0. 2 squared is 4, plus 2 is 6, minus 6 is 0. So if we do direct substitution as it is, we get 0 over 0 as an indeterminate form. What we can do is we can factor the numerator. The numerator factors to x minus 2 times x plus 3. When we factor this, we see that we have x minus 2 as a factor in the numerator and the denominator. So we can simplify this function to be just x plus 3 if we exclude the value that x equals 2. Because we know this function, the denominator can't equal 0, so x can't be 2. However, when we're just doing direct substitution, x plus 3 is a graphically equivalent to our original function, except that it fills the hole at x equals 2. So if we look at the limit as, if we do direct substitution on just x plus 3, and we plug in 2 for x, then we get the limit of our original function. And that's okay, we can do that. So we'll find the limit as x approaches 2 of x plus 3. Using direct substitution, we get 2 plus 3, which is 5. And so this method tells us that the limit as x approaches 2 of our function is equal to 5. Similarly, in the second example, the limit as x approaches 0. If we do direct substitution as it is, we get 0 over 0. That's indeterminate form. No, it's not equal to indeterminate. We don't say equals indeterminate. It doesn't make sense. We just say that is the indeterminate form. And what we're going to do is we're going to factor that. So in this example, we can factor by taking a greatest common factor of x out of the numerator and the denominator. So that's going to be the same as x times x plus 3 over x times x minus 2. So if we cancel out the x factors on top and bottom, we get an equivalent function, x plus 3 over x minus 2. It's equivalent in all values except for x equals 0. The only difference between the graphs is that x plus 3 over x minus 2 fills the hole at x equals 0, which allows us to use direct substitution for this equivalent graph. If we use direct substitution, we get 0 plus 3 on top, 0 minus 2 on bottom, which gives us an answer of negative 3 over 2. So the limit as x approaches 0 of our original function is negative 3 over 2. Third example, the limit as x approaches 7 of this function. If I enter 7, let's see here. We can factor this in like before. The top we get x plus 2, x minus 2, that's difference of squares. The bottom we can factor x minus 3, x plus 2. When we use direct substitution on our simplified function, we plug 7 in for x and x minus 2, and in x minus 3 we get 7 minus 2 over 7 minus 3, or 5 over 4. So our limit is 5 over 4 for this one. And so these three examples together show us that we can use factoring in order to use direct substitution. Now, if we evaluate the limit by rationalizing the denominator, so this is another algebraic trick that takes advantage of the concept of difference of squares. And so we're going to multiply by the conjugate is what this is. So in the first one, if I evaluate the limit direct substitution as it is, I get 0 over 0. So what I'm going to do is I'm going to multiply the numerator and the denominator by the conjugate of the denominator. So the denominator is the square root of x minus 2, so the conjugate would be the square root of x plus 2. And I'm going to multiply that by the top and the bottom. In the top, I'm just going to leave those as like two factors that are multiplied together, so just the two, not the product itself. And the denominator, when I multiply this, is difference of squares. Square root of x squared minus 2 squared is x minus 4. So to multiply those together, I get x minus 4 in my denominator. And you can see that x minus 4 is now a factor on the numerator and the denominator. So I can write an equivalent function. The square root of x plus 2 is a graphically similar function to our original function, except it fills the hole at 4. So when I do direct substitution in our similar function, I get the limit approaches 4. So 4 is our answer. Similar procedure for the second example. We're going to multiply the top and the bottom by the conjugate of the bottom. The conjugate of the bottom is the square root of x plus the square root of 2. When I multiply that out, I'm going to factor this difference of squares, x plus 2, x minus 2, multiply it by the square root of x plus square root of 2. Our bottom are conjugates, they multiply to be x minus 2. I see x minus 2 as a common factor in the numerator and the denominator, so I'll cancel this out. My similar expression, similar, but it fills the hole at x equals 2. I can use direct substitution on this now. Plug in 2 for my x, and I work with some square root symbols here. Square root of 2 plus the square root of 2 is 2 root 2. Multiply by 4, my limit is 8 root 2. All right, so now the trig identities. If there's one trig identity you absolutely know, it's that sine squared plus cosine squared equals 1. So if you may have noticed, my Big Bang Theory meme here uh, is kind of a play off of that Pythagorean identity. So if we look at this thing, we know that if sine squared plus cosine squared is 1, then we can isolate sine squared in that identity and say sine squared is equal to 1 minus cosine squared. So I'm going to substitute sine squared of theta and replace it with 1 minus cosine squared of theta. Cosine squared, or 1 minus cosine squared of theta, is the difference of squares. It's equal to 1 minus cosine of theta plus 1, or times 1 plus cosine of theta. And when I factor out those difference of squares, I do notice that 1 minus cosine of theta is in the numerator and the denominator, and I can cancel those out. And that leaves me with a similar expression of 1 over 2 times 1 plus cosine of theta, which fills the hole at sine of theta, or at theta equals 0. So cosine of theta is equal to, or cosine of 0 is equal to 1. So this is the same as if I use direct substitution in this function, we get 1 over 2 times 1 plus 1, or 1 over 4. So the limit of our original function is 1/4. And we could check that graphically. Let's see here. As x approaches 0, it levels at about 0.25, which is 1/4. And that works. In case you forgot your trig identities, here's a list of some basic ones. And when I say basic, what I mean is that we can use these trig identities to build most of the other ones on any list of trig identity tables. So if I know sine squared plus cosine squared equals 1, then I can manipulate that to find sine squared or cosine squared. If I know the angle addition identities, sine of A plus B, then from there I could figure out the difference identities as well. or the double angle identities. I just use a plus a instead of a plus b. Let's see here. Tangent is and cosecant and secant and cotangent. If I combine these reciprocal identities with the other identities, I can get all of my cosecant, secant, and cotangent identities. So here's a basic list. If you're not comfortable with your trig identities, definitely practice these ones right here. I would say it's not very much, but maybe this looks like a lot. But when you really start practicing these, you'll see that a lot of them kind of overlap and are similar. Try them out. Make some flashcards. Maybe get them tattooed on your face. You pick your poison. All right, so piecewise functions. I couldn't think of a better place to put this one as far as this whole unit. So this is just the lesson that we slap this in here. If I want to find the limit of a piecewise function, what we're going to do is our x values over here kind of tell us what the graph looks like. So when x is equal to 1, the answer is just 2. But when x equals any number but 1, this function tells us what the output is. And that's kind of the general way of how piecewise functions work. So if I want to find the limit as x approaches 1, I would have to figure what would, if I find the limit as x approaches 2 of this function, I'd have to figure out what does 1.99 look like, or as we get closer to 1, and what does 2.001 or 2.0001 looks like. But basically we would be using the top function. What this tells us though, and where this does fit in this lesson, is if we use direct substitution for this piecewise function, f of 1 is, or f of 2 is, if this was f of 1 it would be not really helpful. But we're looking at f of 2, so I guess it doesn't really apply. But yeah, this is kind of what piecewise functions look like. And yeah, so we'll see that on the homework assignment. Takeaways for this lesson. Sometimes we have to do some algebraic or manipulation or working with trig identities in order to use direct substitution. And factoring, even though we're in calculus, this won't go away.